Welcome to the GEOTOP-A online seminar. Our speaker today is Yuanan Diao, who's going to tell us about the braid index and rope lengths of alternating knots. Take it away, Diao.
Thank you, David. Very nice to be here to see everyone. And thank you for the organizers. So let me get started. So the talk is about the rope length and how the braid index can help with the research on the rope length of knots. So let me see if I can turn my page. No, I cannot. So this will not be the most optimal way to do it. Okay, so here's the outline. So I'm going to talk about the rope length, the definitions. I'm not assuming everybody knows all the details, so I will give a little bit of outline and the history. And I will talk about the main topic of this talk, which is a conjecture about the rope length of alternating knots. And then the main tool that will get me the result is the braid index. So I will talk about that briefly. And so, talk about the results, about how the braid index can help me with the rope length. And then at the end, I will give you a very brief proof how this conjecture is proved. So let's see. So when we define the rope length, the basic idea is about thinking the knot instead of just a thin curve, but thinking it as being tied with a rope, right? So a closer rope here has to be closed. It's basically you are thinking about a tubular neighborhood of a smooth closer curve, right? Which is our knot with a given knot type. Now, when I define the so-called thickness of a smooth knot K, this is the smooth closed curve in space, right? So we are thinking about the largest possible tubular neighborhood. And the radius of that is defined as the thickness of K of my knot. So, then once you can define the thickness, the RK, right, for the given knot, the K here has a length, the curve length. So what you do is you take the ratio between the length of the curve divided by its thickness, and that gives you a quantity. And this quantity is a scale invariant. So, and you will define this as the rope length of this particular curve. And once you have that defined, you can then define the rope length of a knot type, which I would just call the knot, right? Basically, it's the infimum of all this knot, right? The rope length of all the Ks that has that knot type. So for example, if you think of the trivial knot, which is this knot here. So if you think this is a unit circle with a radius of 1, right? You can start to expand it, make it thicker and thicker, right? So you can make it thicker and thicker. So you can see at the limit, you can reach this tube here has a limit thickness of 1, right? And therefore, the thickness would be exactly 1 for the trivial knot. And therefore, the thickness of the trivial knot is 2 pi over the radius, which is 2 pi. So that's the minimum. So the rope length for the trivial knot is 2 pi, and that's the minimum. And turns out that's the only example where we know the exact value of the rope length for a knot, which has 1 component, right? So in the case of a link with multiple components, we do know the exact rope length also for a few very simple ones, such as the hop link. And but that's not what I will go, because I'm constantly on the knots, not the links. So determine the exact value of the rope length for any non-trivial knot suddenly seems to be a very hopeless task. And therefore, our research effort in this is really to find basically the estimates of the rope length, such as the upper bound. So you give me a knot, and what is the upper bound of its rope length? What is the lower bound? So we are trying to find the good bounds of those. So in terms of the upper bound, you can achieve an upper bound of the rope length of a knot by direct construction, because you make one, right? You tie one with a rope, and then you can actually measure it. So, and by doing this, you can get results such as this. For example, by computer simulations, you can actually make this knots using the polygons, actually, refined polygons, basically. Using that idea, people have made the trefoil with the rope lengths are the most this. So which means the rope length for the trefoil is at most this number, and as you will see, this number is actually pretty good, and we believe it's much. The real number is not much less than this, and we also know that for some knots, their rope lengths are at the order of their crossing number raised to the 3/4 power. And which means they are, you can tie those knots more easily with shorter ropes. Okay, so let me see if I can change my screens here. I would like to turn my page. Okay, this is better, yeah. So, and in terms of general upper bound, this is probably the best result we know in general. So for any given knot, actually this works for the link too, that the rope length is bounded above by some constant times the crossing number of the link times the natural log of this link raised to the power 5. So this is a log term, a power of log term. And that's basically the best known upper bound for general upper bound. And we don't have any examples where the rope length of the knot links exceeds the order of their crossing number. Turns out we tried actually, but turns out that such example are hard to find. So which means it might be possible that a general rope length for any link is bounded above by the order of its crossing number. It's not going to be less than that, because once you look at the lower bound, you will know why. So on the lower bound end, it is generally a harder question. The reason is that, when you talk about the minimum, right, you talk about the minimum rope length, and the configuration of a knot link in a minimum rope length state, we actually have very little idea what it looks like. And therefore, the minimum crossing number, which you read out from minimum projection, right? That does not give you any structure to work with, because your minimum structure may not look like that. The minimum rope length diagram and the minimum crossing number diagram may not be the same at all, right? And therefore, that doesn't give us a direct help. Here's an example that it's been floating around for a while. At the beginning of this question raised, the question was, if you take a piece of rope with a diameter 1 inch, but the length is 1 foot. In other words, this guy has if the radius is 1, then this would be 2 feet long, right? So the question is, with this 1 foot rope of 1 inch diameter rope, can you tie a non-trivial knot? And even for that simple question, for a long time, it could not be answered. And eventually it was answered negatively. The answer is no, you need more than that. In other words, the rope length for any non-trivial knot is at least 24. And later that was actually improved to at least 31.32. Remember, you saw an upper bound of about 32 point something, right? So you see this lower bound is actually, the gap between the two numbers is not that big. But this one, you have to use something called the quadrisequence, a straight line that intersects your knot in 4 points. And you have to use that result, which is fairly a unique thing, and do some detailed analysis to get this result. And on the general side, so if you talk about the general lower bound for any given knot or link, and this would be a general lower bound. So that is the rope length of any link is bounded below by its crossing number raised to the 3/4 power, of course, multiplied by some constant. This is called the 3/4 power law. And this one is done by using analysis on the average crossing number over all projecting directions. And remember that we also saw earlier on the upper bound result that some knots do have that crossing number to the 3/4 power as they are upper bound. And therefore, that means there are some knots whose rope lengths grow exactly as they are crossing number raised to the 3/4 power. But that's not true for all knots. In other words, there are knots whose rope length is longer than that, right? So some family of them, actually, they grow at the order of their crossing numbers. So there's a gap there. In other words, what we know now is for any knot link, their rope length is somewhere between their crossing number to the 3/4 power to their crossing number, okay? Of all the ones we can construct, okay, in other words. And this result here, this linear order result, is basically by using the fact that the bridge index bounds the rope length from below. All those bounds I'm talking about, there's always a constant, positive constant involved, which I just use a bigger O to make it the presentation a little bit simpler. So, okay, so this is pretty much about the introduction part. And are there any questions at this point? All right, so now let me talk about the conjecture here. So the conjecture here is, let's deal with, consider all the alternating knots and links, right? So the conjecture says, well, for all the alternating ones, our sense, if you actually draw such an alternating guy, you will think that, well, looks like to make this thing to go up and down, in following an alternating pattern, it looks like you need a lot of rope to do that. So the conjecture basically saying, well, the rope length of an alternating guy has to be at least its crossing number times some constant. So that's the conjecture. Now, and this is actually pretty difficult. So here is a challenging question. Here are two examples, right? The two K torus knots and links. Here is one that has one component. Here is one that has two components. So they are alternating. They are very simple. Can you actually prove their rope length is at least some constant times their crossing number? And that would usually be the first examples people look at because they think that if this has a much simpler structure, so there might be a chance to do it. At least I tried it for a long time and I could not have any direct, well, I could not succeed because once you talk about the minimum configuration, you really have no idea, right? Like it looks like what? You can try to tie this thing. For example, you could actually make a configuration like with a two piece of rope, and you can physically try to tighten it. You will know that once you try to tighten it, this thing becomes a blob. It's hard to tell what shape it takes actually. So and therefore, I think the plausible approach has to be that you related the rope length to a knot invariant, and that knot invariant in turn can be related to the crossing number, and that builds the thing because you need an invariant to serve as the bridge. Well, maybe the bridge number would be something that come to mind. The bridge number was something used before. Remember, the bridge number is that, if you look at your knot from any direction in the space, it has to have that. So if the bridge number is a 2, that means from any number you look at the curve, it has to have 2 maximum, 2 minimum, right? And so those maximum minimums, when you think of a rope, those maximum minimums require the rope to turn, and that will require a certain amount of rope to realize those turns, those maximums, minimums. And therefore, it's fairly obvious once you draw the picture that the bridge number is actually a lower bound for your rope length, right? Multiplied by some number. However, that is not a good candidate in general because there are just too many of them with the alternating knots with small bridge numbers. Like those guys here, they all have bridge number 2, but they are complicated enough, right? And their rope length is not short. So the bridge number is not a good candidate. And so when you search for other candidates, that's a quantity you can compute, naturally the Braid index comes in mind. So the Braid index here, here's an open braid with 5 strains. You basically run strains starting from a horizontal bar, you run it down, and here they have directions. So you can make them oriented in the same direction. So in my case here, everything is oriented downwards. Okay, they all point downwards in this case. And then you can close of them using the dotted line here. See, if you can close them, then what you have will be a closed braid, which of course is a link, right? So it is an old result that all the links, every oriented link actually can be represented by a closed braid. It's a very old result. Because of that, we can define the braid index as the minimum number of strains needed to present your link as a closed braid. That's how we define the braid index. In the case that you have a link with multiple components, then remember we're talking about oriented link, right? So if you have multiple components, you can assign different orientations to those components, right? And those different orientation assignments, they can lead to different braid indices. And therefore, I'm going to introduce a notation here. The capital B of K is the braid index of the largest braid index among all those orientations assignments, okay? So the Braid index used to be a quantity, not invariant, that is very difficult to determine. And that remained the case until the non-polynomial revolution happened. And when the Hornfly PT polynomial was discovered, and that gave us the biggest help. So the biggest help we have there is that there's this inequality. So for any oriented link K, its Braid index is bounded below by this bound. This capital E of K is the highest power of the variable A. The Hornfly polynomial has two variables, A and Z, and this is one of the variables, A, right? The EK is the highest power. The lower case EK is the lowest power of A. In other words, this is the span of the A power, right? You take that span divided by 2, which is always an integer, plus 1. So this number serves as the lower bound of the Braid index for this link. And this is a very powerful thing because this is a lower bound. So in a lot of cases, you can construct your a closed Braid representation of your link with exactly that number of strings. If you can do that, then you succeed in determining the Braid index. It would be exactly that number. Or at least you get a bound, right? You get a number, whatever you can do that serves as upper bound. And this number is always the lower bound. So you always get a range at least. So for example, using that inequality, we can now getting, for those torus links, right? You can get the Braid index. For example, the torus knots where the 2 and 2 and plus 1, that's a torus knot. Only one common on the left side. And those guys have Braid index 2. For the two component guys, if you give them parallel orientation, the P means parallel orientations, then they have also Braid index 2. But if you give these two components opposite orientations, then their Braid index changes quite a bit, right? It's actually n plus 1. Remember, those guys have Braid, the crossing number for this guy here is 2n. For the 2n plus 1, the cross number is 2n plus 1, right? So at least in this case, in one orientation, the Braid index is actually bigger. Although now with this tool, we do know a lot of for a lot of links, we know their Braid index, but for most of them, we still don't, right? Because that tool, as powerful as it is, still not enough. Okay, so the Braid index still remains open for most of the knot links. So that's what we need to keep in mind. That including all the alternating ones too. So for most alternating ones, we also don't know exactly how to determine their Braid index. We know they are lower bound by using that inequality, but we actually don't know the exact index. So the next thing I want to do is I want to relate the Braid index with the Ropelength. I want to see how those two things relate. And in fact, I want to tell you the Braid index actually is also serves as a lower bound for the Ropelength. So to do so, I will introduce this lattice embedding of your knots. So the cubic lattice, here's the two examples. So cubic lattice is z to the power 3, right? So the lattice point all have integer coordinates. So on the left side is the trefoil. And here each segment has length 1, and every vertex here have integer coordinates. Okay, and every segment has a unit length. And the right side is a more complicated one. It's an 8 crossing guy. Maybe I think it's 815. It's hard to tell, right? But you can realize you are not on the cubic lattice. The advantage of doing so is that on the cubic lattice, you can actually compute the length easily, right? You can count the number of steps, the segments you use. So, so if you realize you are even not on the lattice, so here I have K of C as my notation. K of C is my lattice realization of K of my not K. The arrow of Kc is its length, and this result tells you that the length of my lattice realization is always bigger than or equal to your largest braid index of your K. Remember, when I realize a link or not on the lattice, that has nothing to do with orientation, right? So here, if you have a link, it is possible you can have different orientations. Therefore, the one I'm using is the orientation I'm talking about is the one that gives us the largest braid index. Okay. So how do you do that? The main idea in this is that you start with your KC, right? You give it an orientation that produces the largest braid index. And then you show that a proper projection of your KC is equivalent to a closed braid diagram in which, it has at the most that many strings. And that's the main idea, right? But of course, it's easy to say and done. So there are a lot of details in that result, which I will not talk about. And there's a side effect. There's a side result here, which I will cite. This is an early result that relates the length of the minimum length of your knot on the cubic lattice. This is what I call LCK, right? You can realize you are not a link on the cubic lattice, but among all of those realizations, you choose the one that has the shortest length, and that's what LCK means. And your smooth knot, the rope length, is always bigger than that lattice length multiplied by some constant. We have a 1 over 14 here, but that number can be improved. I know it can be improved to 1 over 12. It can be improved further, but it requires some detailed work. And so right now, I'm only worried about getting a number. So in other words, the rope length we're talking about and the lattice length of your link, they are actually related. So in some sense, up to a constant, they are kind of equivalent. So, and therefore, if you would using this result, then that theorem we have basically says your rope length is bounded below by some constant times the biggest braid index. That's what I mean by the braid index bounds the rope length from below. So here on the right side is your braid index, and that serves as the lower bound. Any questions? All right. So for instance, if you look at the 2N torus knot, remember it has two components, right? And has you can assign different orientations. One of them with the opposite orientation, remember the braid index was N plus 1. And therefore, the rope length of the right side guy is, by this result, is at least 1 over 14 times N plus 1. Remember, N, the 2N is the crossing number, right? So therefore, if I replace that N by the crossing number divided by 2, then I get this result, right? So now for this would be a very simple proof. Now you can see that for the 2 to n torus link, its Braid index, its rope length is bounded below by its cross number. So that would be approved using the Braid index as the middle bridge. So I have a question here about the constants. You talk about the 1/14. So basically, those constant comes from because to relate the two things, I start from the rope, right? From the RK here. So you have a unit thickness thing in that tube. I basically build a cubic lattice with a small scale so that in that tube, you can fit in the entire cubic lattice realization, but with the smaller numbers. So the step length is shorter. So, and that length, that number comes from in that realization. I don't know whether I made it clear. So you have a tube, right? Doesn't matter how you tube it, how you place it. So or it doesn't matter how you place it in the space. But once you create a lattice, say I believe the step length in that case is like 1/7. Then you can you can prove that they are, you can then make uh, a cubic lattice realizing within this tube. Okay, then you blow it up to make it a full length uh, thing. That's where you get this. That's where you get the ALC, and that's where the constant comes from. Okay, so this is good in some sense. So for a lot of alternating guys, you can do this and find out where their rope length is bounded below by some number of times their crossing number. That's good. That's because in those examples I give here, their Braid index is proportional to their crossing number, right? However, there are ones that have small Braid index. For example, the one on the left side, the Braid index is 2. So no matter how big your crossing number is, the Braid index remains 2. Therefore, at this point, your Braid index can only be of this much help, right? So we stuck. So I got stuck for a long time. You know, this result was done quite a few years ago. And so finally, we now have a new breakthrough and through the talking about the double. So the idea here is I have an alternating knot and I'm going to make a parallel copy of it, like I have demonstrated in this thing here. You can imagine that you take your original knot, you make it into a tubular neighborhood. So on its boundary of that neighborhood, you basically run another copy of it, right? But of course, on that boundary, the knot can wrap around. So you may actually introduce some twist like this. The reverse here means that when I make this link, I assign these two components opposite orientations. That's what reverse means, reversed orientation. This is what I mean by the reverse parallel link of a knot. So, well, how does this help us? You know that you can make infinite many guys like this for any knot. But the good news is that they can be classified that basically two such things are equivalent if they have the same linking number and vice versa. In other words, out of all this, they are all characterized by their linking number. And this is the result that that's the new result that we got last time. This is a joint work with Hugh Morton, and he is the main force behind this result. Here is the formula. That means for if you have an alternating knot K, you can always start from a reduced alternating diagram, okay, from this K, or of this K. Then from this reduced alternating diagram, you can actually calculate the Braid index of this reversed parallel link. Okay, so let me explain the formula. In the formula, there are a few numbers. F in the literature is called the framing, but it's really just the linking number of this link, then you negate it. So it's a negative of the linking number. So negative F is our linking number of the link. So the formula basically says there are two quantities we define, AD and BD. AD is the rise of the diagram minus V minus of D. BD is the rise plus V plus of D. Now, what is V minus and what is V plus? And here is a diagram that explains it, right? So when you have an alternating diagram, it's a well-known fact that you can do a checkerboard shading of the diagram such that all the crossings in the diagram are positive in terms of this shading. So what do I mean by positive in terms of shading? So if you do a right-hand rule, you put your right hand over the over crossing, the over strand, you do a rotation with your thumbs up, right? You will be rotating into the shaded region. That's positive. So you see, in this case, in this example here, I have 5 shaded regions, right, in this shading with all things being positive. And therefore, my V plus is 5. That means when I shade it in such a positive way, my shaded region number is what V plus means. And V minus is the unshaded regions, the number of unshaded regions. In this case, I have 2 of them. That's why it's 2, right? In this case, the rise, of course, is determined by adding all the signs of the crossings. The sign of the crossing here is not this sign here, but it's actually the sign of the by the orientation. Somehow my pin is not working. So if you do the orientation here, you can see those crossings are actually positive crossings with respect to their orientation. So for example, remember the earlier ones. This one basically says that you have your Braid index is starting with CD plus 2. C is the crossing number. Then you look at compare your F and this quantity AD and BD. If F is between the two quantities, then the Braid index is CD plus 2. But if your F is less than AD, then you actually would add the difference. This would be a positive number, right? It's AD minus F, your F is smaller, right? And if F is bigger, well, then you take also you add the difference, whereas F minus BD, that's also positive. So if you have, in some sense, this is telling you if the linking number is within some range, then your Braid index is this fixed number, but beyond some range, you have to add the number of you have to add the more, right? So here is the next one. For example, if you look at this example, so in this example, remember we know the v plus is 5, v minus 2, the rise is 5, right? And therefore, in this case, your A would be 5 minus the 2, which is 3. And B would be 5 plus 5, that's 10. And the linking number here, if you look at the linking number of these guys, if you count between the two components, they are all negative of the 5 here. So they are 5, 10. There are 5 crossings here. At each place, you have a negative 2, right? You have 2 crossings between the two different components. So you count as negative 10 in the middle. And above there, you have plus 4. So negative 10 plus 4, and that gives you negative 6, and divide by 2. That's your linking number. And remember, our framing is the negative of our linking number, so our framing is 3. For this particular guy, the framing is 3. Therefore, your F is between the 3 and 10. And therefore, the Braid index for this particular guy would be the crossing number of the original link, which is 5 plus 2. So the Braid index for this guy would be 7. Okay. Had I had more twisting here, for example, if this guy were like, instead of 2 full twists, if I have 4 of them, for example, this would be negative 5 plus 4, and that would give me negative 1. This would be 1, F would be 1. In that case, your F would be 2 less than the 3 here, and therefore your Braid index, you would have to add the 2, and it would be actually 5 plus 2 plus another 2, so it would be 9 in that case. So 2 more full twists here would bump up your Braid index by 2, and that's basically what this formula is saying. But I explained this because the theorem is significant in itself, not just because of the rope length problem. Because remember, we cannot even determine the Braid index for most alternating knots, right? And here, this result is saying for any alternating knot, you make a double, you give it an opposite orientation, then suddenly we can determine the Braid index. So it's quite a nice result, actually. Now, in terms of for us, though, well, remember the minimum in all these 3 things, right? The 3 formulas I have here, right? Every one is big or equal to the CD plus 2, right? So the minimum of the Braid index is CD plus 2. And therefore, the rope length of the double, right, is bounded below by the crossing number plus 2 for any framing. It doesn't matter what F is. Well, that is enough for me to put up the proof for the to prove that the conjecture, the rope length conjecture for the alternating knot is true. So 4 is the result about the Braid index serve as the lower bound, right, of the rope length. 5 is the result we just talked about about the double. So how do you do this? Well, so let's say Kc is a realization of K on the cubic lattice with the smallest length. Okay, so L of Kc is our smallest. Okay, and then what I will do is I will take a double copy by pushing away the cos Kc by adding the half on each coordinate. So this push it away. So this new copy Kc prime is on this half, is this pushed away cubic lattice, right? It's shifted. So you take the union of the two, well, now you get a parallel link, right? But they are not on the on the cubic lattice yet. So what you do is you double them, right? You multiply the two. You multiply them by two, so every coordinate is multiplied by two. And now the fractions will go away. And now this new copy is now on the cubic lattice. And the total length, well, you double each one of them, you multiply by two, right? So you scale it up by two. Therefore, this double has total length of 4 times L of KC, right? So therefore, by 4, the length of your realization, which is 4 of this, is bigger or equal to the largest Braid index of this double, right? We know this double has some linking, has some framing number in there, but it doesn't matter, right? We know this number is bigger or equal to the crossing number of K plus 2. And therefore, I can put the two things together, right? Because that is bigger than this. Therefore, our rope length is bigger or equal to 1 over 14 times the minimum length of KC, right? Of the lattice realization. And this realization, by looking at here, right? If you divide both sides by 4, you get 1/4, right? So you take the 1/4 times this 1 over 14, you get it 1 over 56. And the crossing number there. So that's the constant we are talking about. So it's 1 over 56. That's our constant times the crossing number plus a little bit more, right? So, and here on the right side, on the left side, that's the rope length of your alternating knot. So it doesn't matter what alternating knot you have. It is always bounded below by this constant times its crossing number. That proves the conjecture is true for the alternating knot. And that's the end of the story. I'll stop here. And thank you.
Excellent talk. So, how about some questions from the audience? I had a question about when you produce this reverse alternating link for that particular, was a 2-bridge knot. You had some crossings at the top, and you can choose those. Yeah, you had 1, 2, 3, 4. You choose those, an even number of them arbitrarily. I mean, what? Why are they any crossings at all up there?
They are, I just used one of them as an example. It doesn't matter. You can have as many as you want, right? They will have different, Braid index. So those, when you add in this twist in there, it changes what this F you have down here. And that in turn will affect the Braid index. Remember, you can make many doubles, right? You can make many doubles. So this is just one of them.
Yeah.
And so, but they are all, if you have 2 of them, they have the same linking number, then they are equivalent. And the Braid index, of course, then would be the same, right? So in the formula, you can see it basically only depends on their linking number.
Cool. Suppose you look at knots which are almost alternating. They have a projection where all but 2 crossings are alternating.
Uh-huh.
Can you do anything with that? I mean,
So the answer is, in general, the answer is no, because once we push the general, this mechanism here only works, this double approach only works for alternating knots. It does not even work for alternating links. In other words, the conjecture is only proved for alternating knots. If you have more than one component, this is off. Yeah. So, yeah. So I see here there's a question here in the
Sorry, I
chat.
was told to ask it out loud. So if you, first of all, big fan as one of the other 4 rope length guys. Um, so if you replace the corners of your cubic lattice knots with arcs in a way that doesn't interfere. Is there a way to make a small improvement to the bound?
Yeah, certainly. Yeah, those are the details I left out. So the bound can be improved quite a bit, I think. So there's a lot of room there for improvement indeed. And if you wonder like how much I would guess you can improve, it's hard to say. I would
So,
hope that for something like 1/10 or 1/2, something like that.
so when I did a bunch of rope length simulations of these satellite knots, and we showed that when you basically you increase the rope length by a factor of 3 when you double the knot like that.
Mhm.
That's just numerical.
Mhm.
So that gives an effective exponent of log 3 over log 4, which is 0.79, but that's just numerical. It doesn't prove anything.
Yeah.
Okay, are there any other questions for our speaker?
Um, Hi, could I ask the question? What is the trouble that I should get into if one try to double the link to produce the reverse parallel link for a link? What the trouble be?
Can you repeat your question? I didn't not quite get it.
What is the trouble if one tries to make the reverse parallel link for a link?
That's just we so the rope length does not depend on orientation, right? So if I double it, the idea is that from the double, I can give it different orientations in the hoping of getting a large braid index. Because I know my braid index is the only tool I have to serve as a lower bound. So unless somehow I can get a large braid index that is bounded below by the cross number, otherwise I have no hope, right? And that would be one thing I can think of. That's just, so when you double it, you double the length in some sense, right? You make a double, but it's a linear sacrifice. And that's what happened at the end. Does that answer your question?
Thank you. Yes.
Yeah, because if I don't double it, I know there are a lot of examples where the alternate knots have a very small braid index, right? Which does not really help me at all. So one thing one can also wonder is that what happens for the alternating links when you have more than one component. So this approach fails. Right now we actually don't know how to get around to extend this result to alternating links. But from my experience, like looking at the two bridge links, for example, the one earlier, right? The 2N1. So if you look at the two bridge links with two components, at least for those guys, we know the conjecture is still true. And I think more generally, even for alternating Montesino links, we know the result is also true. And those are large classes of alternating links. So I think I'm pretty sure the conjecture actually is true for alternating links. We just don't know a way to get it yet.
Okay, well, hearing no other questions, let's give our speaker a round of applause. Well done.
Thank you.